Don Pirjol from Stevens Institute of Technology. The title of the presentation is W-shaped implied volatility curves and the Gaussian mixture model.
So I hope the sound works. Can everybody hear me? Okay.
Sound good? Yeah.
Okay, thank you. Thank you very much to the organizers for the invitation to give this talk. So I've known Peter maybe for almost 10 years now. I worked in industry for the past 10 years before joining Stevens in 2019. And I interacted many times with Peter. So probably the most memorable interaction was when I was working on one of our models at JP Morgan called Carr randomization. That's based on Peter's method for pricing American options. So my task was to poke holes in this model. So naturally, the first idea was get in touch with Peter. So actually, he told me many things about the weak points of the model, how to improve them. And so someone who works with quants immediately realizes that they're not very eager to tell you the weak points of their models, but Peter was different. And yeah, we all know he was very special. So we continued to keep in touch. And then I also moved to academia. We continued to discuss. So today I'm going to tell you about some recent work, joint work with Paul Glasserman from Columbia. I'm sure Peter would have liked to have enjoyed this work. We actually use some of his results. It's not working. Am I doing this the right way? So I'm pressing here. Oh, it doesn't work?
No, this should work now.
Oh. Thank you. Okay, so this is motivated by some recent shapes we see in the option markets, event-driven implied volatility shapes, which are very intriguing. So we try to get a better understanding of the implied volatility shapes and how they relate to the risk-neutral density. And we have a new approach to do that. Then I will discuss as an application the Gaussian mixture model, very popular model in practice. And the work is already available on SSRN. You can check out the reference. Okay, so I'll be talking about options, implied volatility, very well-known concepts to everybody here. So traders prefer to parameterize option prices in terms of a volatility surface, which you can pull down on Bloomberg or your favorite system. That's the shape of a typical volatility surface. This one is for Amazon on a regular market day, typically U-shaped or with a skew and flattening out in the long maturity limit. But sometimes these shapes can get very strange. As we heard yesterday in the talk of Dilip Madan, after 2009, option markets are much better developed. Many more strikes are being traded. So now we have access to the volatility smile over a wider range and with a much finer grid. Sometimes we see these kind of strange shapes, which are pointed out over the past few years by Vola Dynamics and others. And this is an extreme case, which was discussed in a blog post on Vola Dynamics as the most interesting vol surface in the world. This is Amazon, options on Amazon with 1 day maturity, just before market close and before earnings announcements. So clearly this uncertainty in the announcements, the earnings announcements, distorts the shape of the smile, which now becomes concave at the money point, and even W-shaped. This is what I'll talk about when I say W-shaped smiles. So this is extreme, but we see similar shapes in other names, Apple and Facebook, again, just before earnings release. The smile is distorted, concavity at the money, and other than that, the smile rises up in the wings. The academic literature took up these observations, and a more systematic study of concavity of the smile at the money was done by Alexiou and collaborators in a recent paper. They studied the percentage of names with at the money concave smile as a function of time as we approach the earnings announcement day. So our earnings announcement is the day, and the names become, more and more names become concave, only to drop off after earnings announcement. So they interpret this as the reflection of a bimodal risk distribution for the underlying price just before the earnings announcement. Why would that happen? Well, because the market doesn't know yet how to price the stock. Earnings good, the stock price will go up. Earnings not so good, maybe the stock price will drop. So that the simplest way to describe that situation, this ambiguity, is a bimodal risk neutral distribution. We see something similar in March 2020, at the time of the COVID crisis, when it just hit, and the market was pricing two scenarios. The pandemic will impact the equity prices negatively. This will look like the green component, low stock prices, or maybe it will go away and will not have a major impact on the market. That will be the orange or the red peak. Again, a bimodal distribution. The sum gives a bimodal risk neutral density. So this is observed from index options on S&P 500 with maturity December 2020. Okay, so there's this idea that W-shaped smiles or at the money concavity reflects a bimodal risk neutral density. So we investigated this in more detail, asking the following questions. What properties of the risk neutral density guarantee a normal or U-shaped smile as it is in the regular market periods? Does a W-shaped smile necessarily imply a bimodal risk neutral distribution? And vice versa, does a bimodal risk neutral distribution imply a W-shaped smile? And more generally, what can we say without any calculations? If someone gives you the shape of the implied volatility, someone gives you the Gaussian mixture model, which is a generalization of the situation with multiple outcomes, different scenarios with different probabilities, what can you say about the shape of the implied volatility smile? And the way we do that is by looking at the smile through its level crossings. So I'll define the number of level crossings of a certain level as the number of times horizontal line crosses the smile. For example, if you look below the lowest volatility of the smile, the number of crossings is 0, but then as you increase the level, it may cross 2 times, 4 times if the smile is distorted. And the main result was to find upper and lower bounds on this number of crossings if you are given the shape of the risk neutral distribution. So let's see how that works. Okay, we'll fix a maturity. I'll always work with a fixed maturity. The risk neutral density corresponding to that maturity will be denoted F sub S. The expectation of the asset price under this distribution is just the forward price. And then I'll look at a log normal distribution with the same mean as the forward price and the volatility V. And denote the N vol the number of times the implied volatility under S crosses this level, and NPDF, the number of times the density of the reasonable density crosses the density of the log normal. And there's an inequality between these two numbers, which is an upper bound on the number of crossings of the smile. The number of crossings of the smile with a certain level is bounded from above by the number of crossings of the reasonable density with the log normal density. So this is the upper bound. What does it tell us? For example, let's look at the U-shaped smile. U-shaped smiles have single sign change. They are decreasing and then increasing, or vice versa, if it's upward U-shape. And we call it W shape if it has 3 sign changes. So if someone gives us the number of crossings of the reasonable density with the log normal, and that's 2, this density is crossed exactly twice, then we can tell immediately that the implied volatility will not cross that level V. If the density is crossed 3 times, then the implied vol crosses only once, and so on. So that tells you that to have a W-shaped implied volatility, you need to have a very wiggly reasonable density, which crosses a log normal at least 6 times. So it must wiggle around the log normal. It's very unusual reasonable density, but apparently this is realized under certain conditions. Now we have also a lower bound on the number of crossings of the implied volatility with a level, and that follows from matching moments under the reasonable density and under the log normal. Suppose you match several moments. They don't have to be integer moments. They could be real moments. Then one can prove a lower bound, that the implied volatility will cross that level of the log normal at least m times, as many moments you match. They don't have to be moments. They can be any strictly convex payoffs, a square function, or any favorite convex payoff. So now the argument uses the Carr-Madan formula, and it's so simple that I would like to go through the steps for the particular case of matching one single moment. So this is how it works. Let's suppose that the same payoff is priced equally by our reasonable density and by a log normal. For example, the payoff could be x squared or any convex payoff. Then you can take this function, the difference of the option price under the reasonable density and under the log normal with volatility V. And we see that as you change the strike, this function should vanish at the point where the smile crosses the level V, because the option prices are equal at that strike. Now the Carr-Madan decomposition gives any payoff or expectations thereof as a linear combination of calls and puts with appropriate coefficients, which are just the second derivative of the payoff. You can do that both for the reasonable density and for the log normal. And taking the difference of these two expectations, this can be represented as an integral over this function I introduced earlier, h sub v. Now this difference is 0 by assumption, because the two payoffs are priced equally, and the payoff is positive, so the second derivative is positive. The only way that the integral can vanish is if the function h sub v has at least 1 0. So that proves the claim. The implied volatility crosses this level V at least once. This can be generalized to several payoffs. This is a bit more technical, but the same idea. But we can use this result to generate generalization of this W-shaped smile, unimodal reasonable distribution, which has a smile crossing a level infinitely many times. And this is how it works. It has been known for a long time that the log normal distribution is not determined by its moments. An explicit example was given of a function which has of a density which has exactly the same integer moments as a log normal, but it's different from a log normal. That is shown in the left plot as the orange curve. It wiggles around the log normal. Now, if we assume that the residual density is given by this type of distribution, we match an infinite number of moments of a log normal. And by the lower bound, we predict that the smile should cross the level V an infinite number of times. And that's exactly what we see in the right plot. The smile wiggles up and down and crosses the level many times. Of course, a very unrealistic smile, we'll never see that in the markets, but it just goes to show that the modality of the Riesz-neutral distribution is a poor indicator. It's not an indicator of the shape of the smile. You can have a nice unimodal Riesz-neutral distribution, but the smile can be very can cross infinitely many times a level. So what have we proven so far? Let me summarize these results before I move on to the next step. We have an upper bound on the number of crossings of the smile with a horizontal level in terms of the number of crossings of the density, the Riesz-neutral density with the density of a log normal. In particular, W-shaped smiles require Riesz-neutral density which crosses at least 6 times a log normal. There is also a lower bound on this number of crossings in terms of the number of payoffs which are priced identically by our Riesz-neutral distribution and the log normal. And in particular, the modality of the Riesz-neutral distribution is not a good predictor of the smile shape. And we have an extreme counterexample which where an unimodal distribution has a smile which crosses the level infinitely many times. Now, if we want to get more precise and make more predictions, we have to get more specific, build a model, a parametric model for the Riesz-neutral density. And the natural choice when you want to describe multiple outcomes, outcomes for the stock price in the future is a Gaussian mixture model, which assigns different probabilities to different log normals. It's a mixture of log normals, or equivalently, the log of the stock price is a mixture of Gaussians. Now here we can make more definite predictions. This is a summary of the results. I'll not have time to go through all of them, but you can see them in the paper. So I'll go briefly through all these points. For this model, the upper bound on the number of crossings of the smile depends only on the number of mixture components. And the lower bound can be used to give predictions for the range of the implied vols in the model. We also make predictions about the tail asymptotics, what happens to the smile in the large, very small strike regions. And then we make predictions for the dependence on the mixture parameters. What happens if the mixture parameters are more spread out, more narrow? What is the impact of the dispersion of the mixture parameters on the shape of the smile? And as an application, I'll give a complete classification of all the smile shapes which can be generated by the 3-component Gaussian mixture model. Okay, so the Gaussian mixture model must be well known. Under this model, the log asset price is distributed as a mixture of n Gaussians, each of them with its own weight, the probability that you realize that state. And there are constraints from matching the forward price. Of course, from the weights have to add up to 1. And the reason people like this model is that you have a closed form pricing formula. Option prices are just linear convex combinations of Black-Scholes prices. It's used in practice. In particular, Bloomberg uses this for their representation of the volatility surface. It was described in an article in 2002 by Brigo Mercurio, who extended it to a local volatility model. So now we can ask this question. Suppose someone gives you a mixture of combinations. What can you tell about the shape of the implied volatility without going through the calculation? So here is one first result. This comes from the upper bound on the number of crossings. If you have n components, a Gaussian mixture with n components, all of them with distinct volatilities, then the smile can cross any horizontal level at most 2 times n minus 2 times. So in addition to the upper bound I proved earlier, this uses a result due to several authors on zeros of linear combinations of Gaussians. They proved the bound on how many times a linear combination of Gaussians, and the number of zeros of a linear combination of Gaussians is bounded from above by something related to the number of Gaussians. In particular, a very surprising result, if you plug there n equal 2, you get that the number of vol crossings is less than 2. So no way you can get a W-shaped smile. So it's incorrect to say that the bimodal distribution can give you a W-shaped smile because it can at most produce 2 crossings. It will produce a U-shaped smile, but not, or some more complicated shapes, but not a W-shaped smile. Turns out you need to, the market is pricing not only a low price state and a high price state, but also some middle price state. You need at least 3 components to produce that W-shaped smile. And of course, if you go through the calculation, plug in the 3 component smile into the Black-Scholes formula, you get these W-shaped smiles as the weight on the central component is changed. Then the smile moves up and down. The distribution is either bimodal or unimodal. So there is no one-to-one correspondence between the modality and the shape of the smile. So this is a W-shaped smile. It's one of the curves on the previous plot. And we see the crossings of the densities. They cross exactly 6 times as required. So it is kind of a natural smile to have because the density has to have a very specific number of crossings. I mean, a minimum number of crossings. All right, so we also have results for the tail asymptotics. What happens for very large, very small strikes? They all approach a common value given by the maximum of the mixture of the volatilities of the mixture. So regardless of the weights of the components, you only need to know the largest volatility component and you know the asymptotics. Now, how do you approach the asymptotic limit? That requires more information, where this component with max vol is placed. You can place it to the right, to the left of the forward, get different shapes, different approaches, but the only way to approach it from below in both cases is by placing it exactly at the forward. I'll not go through the proofs. They are based on the extreme strikes asymptotics of the Black-Scholes formula. The proof is in the paper. Okay, I'll skip that. So now another question is what happens to the smiles as you change the mixture components? So 2 particular mixtures are more important. You can mix different components with the same forward but different vols. This is what you get when you approximate uncorrelated stochastic vol models in terms of mixtures. Or you could have location mixtures where the volatilities of the components are all the same, but their means are different. So here we can make stochastic comparisons. So I'll remind you inequalities in stochastic order, increasing convex order and convex order. We say that 2 random variables are ordered in the relative sense, in each sense, if the expectations of appropriate functions satisfy these inequalities. So here's a typical result we get. We can compare smiles of different location mixtures, which are more spread or less spread out, by representing the location mixture with a random variable taking discrete values with the same probabilities as the mixture probabilities, then we can prove statements of this form. Comparing the mixture random variables in increasing convex order gives inequalities among the smiles. And this is our typical behavior confirmed by numerical tests. So that's an easy way to compare two smiles if you are only given the mixture parameters without any calculation. All right, so a particular mixture is a symmetric mixture where we have pairs of components related with same volatility and appropriate weights such that the forward condition is satisfied. In this symmetric mixtures, the smile is symmetric in log strike. And we can combine all these constraints on the number of crossings, symmetry, and extreme strikes asymptotics to show that there are only 4 distinct smile shapes with 3 Gaussian mixture components. Well, the first one is the typical U shape. Then you can also get W-shaped smiles, and you can also get this very exotic looking shape, WM shaped. But the constraints I showed demonstrate that these are the only shapes you can generate with 3 components. Still, it's a lot of flexibility to fit any smile we see in the market. All right, so how well does it work in the practice? Here are some fits with the Amazon W-shaped smile I showed earlier, 1-day maturity. So this is a symmetric fit, and then this is an unconstrained fit. The only constraint comes from fitting the left wing of the smile. This is a bimodal distribution, and the fit is reasonably good. So in conclusion, I would say that the Gaussian mixture model it gives you sufficient flexibility to accommodate even these exotic smile shapes. All right, so these are the conclusions. I'll not go again through them, except to say that bimodal density does not imply a W-shaped smile, and also vice versa. And in fact, modality is a poor indicator for the shape of the smile. And we have a few results which show the utility of analyzing the smile through the number of crossings with a horizontal level. So I hope this will be of, we hope this will be of use to modelers trying to model these exotic smile shapes and to get a better understanding, qualitative understanding of the relationship between the shape of the smile and the residual density. All right, so finally, I would like to advertise a tribute to Peter, together with my collaborator Ling Zhongzhu from Florida State University. We are organizing a special issue of the Risks magazine, of the Risks journal, dedicated to Peter, and I'd like to advertise this if there are any people interested to submit articles. I'll share the link. There is still time. The deadline is October of this year. So please get in touch, send me an email, or we can chat over coffee if you are interested. Thank you very much.
Thank you for a very interesting presentation. I don't have time for questions at this time, but if you want to forward down the very thank you again.
Okay.
Our next speaker will be Prithvi